The Ukrainian AI community used to create, develop, and educate for a shining future. But then Russia ruined our peace. We switched to a new reality. We do our best to defend our country. The brightest AI minds came to share knowledge with us. Together, we will build a technological and secure future. Peace in Ukraine equals peace in the world. Support Ukraine. Support the AI community.
Welcome everyone. Welcome guys. And what's we are getting ourselves into? It's a series of AI-based events. We asked a lot of renowned international speakers, very cool ones, to help to support our local Ukrainian AI community by providing lectures and workshops on a variety of topics. And we are also collecting money for our army, and we already collected almost 300,000. So why I'm telling almost, but basically you could donate money during this workshop and we'll hit the target. So all that money will be donated to Ukrainian Foundation Come Back Alive. So welcome. I will be moderating this session. My name is Olesya Stetsuk. I'm data scientist for SoftServe. Just a few words about me. I've been in love with machine learning data science for more than 7 years. And having a background in physics, I do think it's what's kind of predefined for me to fall in love with this field. Today we are having a very important topic from my experience, because we all could, use the most state-of-the-art-ish models and stuff, but all our work narrows down towards validation and evaluation, the results of what we've basically done. And today we have a talk evaluating machine learning models and their diagnostic value. In several minutes, our speaker will be online. It's Gaël Varoquaux. I'll talk a bit more about him if you are not very familiar with him. Meanwhile, we want to make our session as interactive as it could be. So let's try a poll session. So you could ask questions at slido.com. Just put it in your browser and put the code AI for Ukraine, or just go into the link below the video and ask your questions, and the speaker after the session answer everything. Also, if you like some of the question like a lot, you could upload it. And the more upvotes the question gets, the more probability that it gets answered. So let's try this tool together. There is a poll already about which will help us to understand a bit more basically who is attending an event like this one. What's your experiences? So there are two questions in the poll. The first one is about how many years are you in the field? And the second one, what is their area for your work or research interest? What are the main areas for that? Please answer. And after you all answer, we'll get the picture who is with us today. Okay. So what we have at the moment, I do understand like you are still answering, but at the moment we have a lot of fresh people, a lot of newcomers with 1 or 2 years of experience, and a lot of less experienced colleagues, and like around 10% of 5+ years experience. Cool. Wow, that's that's very interesting to see, like who we having on this meeting. So I talk about your main areas. Computer vision, yeah. I do think like everyone expected it. Others. So what we have here is that computer vision is a leader, and other stuff it's very different. It's like diverse. It's merged a lot of the topics in under one name. Recommendation system. Wow. Quite a lot of people from that. NLP, MLOps. Thank you guys, MLOps, also for joining. And a bit of speech processing and reinforcement learning. Okay, cool. So we have a lot of computer vision engineers around here, and I do think that like it's kind of a distribution. It's very common distribution what we are having in our area. Thank you guys a lot for asking. So during their session, you please put your question with this tool, and Gaël will answer those. A bit more. I will ask Gaël in a few minutes to join us. A few words about our speaker. So basically, I do think you all know Inria. It's a very famous French research institute, and they're famous by doing a lot of profound stuff, profound research activities. And Gaël is research director there, with a bit of focus on data science and health. And his research is focused on statistical learning tools, mostly for social science and health. For example, for you to understand a bit more, to have a bit more details, since 2008, he has been exploring actively data-intensive approaches to understand brain function and mental health. Kind of cool. What is also very important part of his everyday work, he literally makes our work as a data scientist easier, with building building software and toolkits and tools to put together all this heavy and kind of complex statistical models without proper tools, without proper software. They might be too complicated to use them in our everyday work. And Gaël is the one who helps to bring the bridge for us. And if I ask you a question like, have you been using scikit-learn like yesterday or last week? Probably a lot of you will, except for MLOps guys, probably, but a lot of you will be like, I did. And Gaël is the one who is co-founder of scikit-learn. So it's helping advanced machine learning a lot, like immensely. And also, he graduated from École Normale Supérieure, and what's like cherry on the top, he has PhD in quantum physics. So like it's for you to understand, to welcome Gaël. It's for you to understand who we are having now. And Gaël, please continue with your presentation. And I hope everyone is just interested as I am here. So welcome. Thank you.
Спасибо большое, Alicia. Добрый вечер, люди. Извините, я не говорю по-украински, so I'll continue in English, but I'm very happy to be here. So today I want to talk about something I believe also is very important, and my talk is meant to maybe get you thinking a bit about how you can evaluate well your machine learning model. And I talk about their diagnostic value because a lot of this talk is inspired from applications in health, but I believe it carries over to many other places. So Oops. Yeah. So I want to cover two things. I want to cover the choice of performance metrics, and I'll take some examples. I won't be exhaustive, and I'll cover some things to keep in mind when choosing performance metrics. And then I also want to cover evaluation procedures. So the important point about performance metrics is that they must capture and they must refer the application. And one reason why it's very important to choose well the performance metric is that the typical machine learning engineer or machine learning researcher focuses on improving this metric. So if the metric is somewhat disconnected with the application, then the improvement is not meaningful for the application. And so I'll start with very basic settings for binary classification metrics, and then I'll show a bit how we can think about these and how they map to the application. And so the simplest one, the most common one, is the accuracy. So just counting the fraction of errors. We like it because it's a very simple summary, but one danger is that it gives an overly simplified picture. It may be important to distinguish the false detections from the misses. So for instance, if I'm looking at brain tumors, is a false detection really bad? Well, it's terribly bad if it leads to brain surgery, because brain surgery is something dangerous. But a false detection of a brain tumor is minor if it leads to a confirmatory imaging. So what we see is that the relevant cost, which corresponds to in some sense, the error metric we're interested in, depends on the application setting. Even for the same problem, depending on how we're set in an operational setting, we might want to trade off false detections from misses or vice versa. So in binary setting, the way to think about this is the confusion matrix. So the idea being that on the one hand, we have the truth, and I'll set myself in healthcare settings, so I'll call the truth the disease status. And then the other hand, we have the prediction. So I'll call this the test result. And so here I'm counting on my test set, for instance, I'm counting how many times I've had true positives, false positives, false negatives, and true negative. And this is basically the full picture in terms of errors on my evaluation set. And so then I can look at metrics that separate the positive and the negative class. And one thing that I forgot to mention is that everything I'm discussing today is summarized in a book chapter that I wrote with Olivier Colliot and that you can find on my website in the publication page. So that's freely available and that is meant to be didactic. So I can look at the metrics on the positive and the negative classes, and here I have the sensitivity, sometimes called recoil, that counts the fraction of positive samples that's retrieved. And I have a similar thing for the negative samples, and we call it the specificity. Now I have other metrics, such as the positive predictive value, sometimes known as precision, which is the fraction of the positively classified samples which are indeed positive. So here, the difference between the sensitivity and the precision is that we're normalizing differently. Okay, on the one hand, we're normalizing by the fraction of positive sample, and on the other hand, we're normalizing by the fraction of positively classified sample. And we have the same thing for the negative samples. Okay, so maybe it's a bit confusing, what's the link between sensitivity and PPV? And the way to think about this is that if I denote T, the prediction, so the classifier output, and D, the disease status, the first two metrics estimate the probability of the test given the disease. So the probability of the prediction given the truth. Whereas the two ones below estimate the Bayesian conjugate, so the probability of the disease given the test. Okay, and that's why we have two different normalizations. I'll come back to this. Okay, so now I'm going to consider the setting of imbalanced binary classification. So if I have very imbalanced classes, for instance, if I'm looking at a somewhat rare disease, so most of my individuals do not have it, I have 90% of class 0. Or if I'm looking at a rare marketing event, I only sell something to 10% of the people who visit my page, which is actually a lot. In this sense, accuracy is not very informative, because always predicting class 0 gives me an accuracy of 90%. So it might be more interesting to look at something else. And once again, we can look at distinguishing the errors in class 0 and class 1. So looking at sensitivity and specificity. And then we can look at the average of the two, the mean of the two, which is called the balanced accuracy. Now, I'd like to say that there's another way to look at this, which is that we're asking the wrong question. If we're looking at specificity and sensitivity, we're looking at the probability of the test output, so the probability of the prediction of the classifier given the ground truth, given the actual value of the class. But what we're really interested in is the probability of the actual value of the class given the output of the classifier. And this is the positive predictive value. And we can relate it to the sensitivity and the specificity simply using Bayes' theorem, some simple algebra, which I've written here. So the probability of the disease, so the ground truth given the test, is related to the sensitivity and the specificity. However, we can see that the prevalence, which is the fraction of class 1, comes into this formula. So what we're really interested in quite often, which is the positive predictive value, actually depends not only on the sensitivity and the specificity of the classifier, but also on the prevalence of class 1. So that's one reason why we don't use it a lot in machine learning, because it characterizes not only the classifier, but also the data set. However, in terms of application, I claim it's more interesting. Now, there is a way to go a bit further, which is a bit more advanced and not used a lot in machine learning. It's to use odds ratios. So odds ratio are used a lot in health, and the definition of an odds is the chance of the event divided by the chance of not the event. So it's basically another way of looking at probability. If we have a 50% chance, odds of 1, and then odds go from 0 to infinity. And the nice thing about odds is that odds ratio are invariant to sampling. And so for this, we can introduce the what's known as the likelihood of the positive class, which is the ratio between the odds of the disease given the test divided by the odds of the disease. So it's often said that it's the post-test odds divided by the pre-test odds. And so this, somewhat by magic, is actually independent of the prevalence. It's only related to the sensitivity and the specificity of the classifier. So this can be used to reason even in the presence of class imbalance, and also even in the presence of class imbalance that varies. And this is a fairly common setting, that the class imbalance varies. People are more likely to buy on certain day than others. The prevalence of a disease such as COVID, for instance, will vary across time. And so this metric, likelihood of positive class, is actually really useful to evaluate a classifier in presence of imbalanced classes that may vary. And so we've added it to scikit-learn recently. It's in the development version of scikit-learn. Okay, now I want to go a bit further, and I want to discuss multi-threshold metrics for classification. And the idea being that classifiers typically output continuous scores. And we threshold these scores, we choose a cutoff to transform this continuous score into a binary decision. And so a classic way of looking at the various cutoffs possible is to vary this cutoff, is to vary this threshold, and look at how our error metrics are varying. And so if we take a cutoff, if we take a threshold that is very, very low, we might make no positive detection. We're classifying everything as negative. So in this setting, we're going to have a very low false positive rate, but we're also going to have a very low true positive rate. And so then we can vary this and we can increase it. And each time we look at how many false positives we do and how many true positives we do. And as we vary this, we get a curve that we call the ROC curve, the receiver operating curve. And here, a classifier that does a decision at chance has a curve that's on the diagonal. And the better the classifier is, the more the curve is close to the upper left corner. Okay? Now, one of the drawbacks of the ROC curve is that when the classes are very imbalanced, everything is somewhat on the upper left corner, and tiny chances to what matters to us, which is the precision or the PPV, make very little difference to the ROC curve. In which case, it's useful to look at the precision recoil curve that's also obtained by varying the threshold, but that's looking at the precision as a function of the recoil. And here, unlike with the ROC curve, the value of the curve under the chance actually varies depending on the prevalence of the positive class. And so typically on those two curves, we summarize those curves by taking the area under the curve where bigger is better. Okay, now we can go one step further and we can look at this non-thresholded value and we can try to see if it has a meaning that we can understand. And so this non-thresholded value, which I will call the classifier score, one question is, can we interpret it as a probability? And this is a question that is related to calibration of classifiers. And calibration of classifiers looks at whether the average error rate for all sample with a given score S is S. So, to give an example, if I look at all the samples for which my classifier has given a score of 0.7, my classifier is said to be calibrated if 70% of these samples are of class 1. And we can look at calibration with a calibration plot, which look at it computes the error rate, the observed fraction of positive on a bin, on a set of bins, on different bins on the mean confidence score. Okay, and it tells us if the classifier is overconfidence, if it's predicting confidence that is above the observed error rate or underconfident. Now, an important point is that the calibration does not control individual probabilities. it controls the average error rate. So our classifier may be very unfair, and it may make much more errors on one subgroup than the other. So it may attribute a score of 0.8 to a group, but in this group of individuals, it never gets it wrong on half of the individuals, say the woman, and it gets it correct only 0.6 times on the man. In which case it's still calibrated because on the group, it's doing an error rate of 0.8. So that's a very common misconception, is that people believe that, or they, in their mind, they don't make the difference, and they think that if a classifier is calibrated, they can trust the individual probabilities. And that's not the case. It's very important to keep this in mind. So now there's another metric that judges how well the classifier score approaches the true individual probabilities. So does the classifier approach P of y given x? And this metric is the Brightest score, which is basically the mean squared error between the true label, y, which is binary, and the predicted confidence score, S, which is continuous. And the Brightest score is minimal when S is the true probability of y given x. Now, the one challenge is that it's minimum, but we don't know what the minimum is. So if I tell you I have a Brightest score of 0.1, you don't know if you're optimal. The optimal Brightest score is not always 0 because you might have some intrinsic randomness, intrinsic stochasticity, which means that I cannot perfectly predict my output given my input. It's often the case in health, in marketing. It's actually less the case in computer vision on high quality images. So this is why it may be also interesting to look at both the Brightest score. The Brightest score, we can use it to select the best model, to take the model that has the best Brightest score. And then, so we know we have the model that's the best, that has the best Brightest score. It's the out of a family of model that we tested, we're taking the one that approaches best P of y given x. It's the best probabilistic prediction that we can make. And then we look at the calibration error, which is something that we can interpret in terms of an error. And we know that a perfect curve, a zero calibration error, is the best that we can get, even though we do not know whether there isn't some unfairness in our classifier. Okay, so this was just a short introduction to some things we may want to keep in mind when choosing metrics. I've chosen the very simple setting of binary classification, and I hope that I've shown you that even in this very simple setting, there's still a lot to think about. And it's a more general problem. You know, we're optimizing metrics. We want to choose these metrics so that they really are optimal for something that works well for our application. And I typically think that we often want to worry about the probability of the disease, the ground truth, given the prediction, the classifier test. And typically, because it's easier, we look at the Bayesian conjugate. And as long as the classes are reasonably well balanced, accuracy and the metrics that we typically use are a good proxy for this probability we're interested in, but that's not always the case. More generally, I think that we need to worry about uncertainty, and here we can look at calibration, but we need to keep in mind that it quantifies average errors and that we might have some form of unfairness, some errors that are very different on the different groups. And for this, we should always do model selection based on Brier scores. And a more general recommendation I have is that a single number never tells the whole story. We are going to have inhomogeneities. We are going to have to worry about different errors on the positive class, on the negative class, and things like this. Okay. Now I want to switch to something else, which is we've now chosen a metric we're interested in. We're interested in choosing the best classifier that gives us the best expected error according to this metric. How do we estimate the error rate of a classifier? And here, so once again, I'd like to show you that maybe there are a few things we need to keep in mind when we're doing this. And the first thing that I'd like to stress, and that's a very important point, is that there are different scenarios. We might be benchmarking a prediction rule. So we're given a function f that is a prediction function. It goes from x to y in scikit-learn words. With the scikit-learn API, it's model.predict. So we're given a fitted model. This, by the way, may not come out of a machine learning model. It may be made by a set of experts. We have a lot of this in health. So we're just given a prediction rule. And so there's another scenario, which is we're given a training procedure. So it's a procedure that outputs a prediction rule, F, from training data. So set of data with X and Y, set of labeled data. And so in scikit-learn API, here we're evaluating model.fit and model.predict. And those are different application settings. So scenario one is basically what I do before I want to put to production, or if I have application claims, as in medicine or in marketing. Scenario two is if I'm doing machine learning research or development, and I want to have conclusions on choices of algorithms. And I'll go a bit more in detail why those are two different settings and why they lead to different procedures. The first point I want to make, and I suspect you're all aware of this, is that we cannot evaluate a model based on the data that has been used to fit this model. And here I'm giving you an example where the orange points are the data that were used to fit the model. The blue wiggly line is the fitted model. It gives me a perfect fit to the orange point. But it generalizes extremely poorly to new data points. So this is why we always look at the error of the model on a left-out test set that has never been seen by the model during training. And so typically, a good choice of how much data to leave out is to leave out 10%. It's a rule of thumb because we need to trade off better learning, so giving more data to the model in the training set versus better estimation of the error. Okay. So now I'll first detail a bit what we can keep in mind in terms of evaluation of prediction error. And maybe a first conceptual point is that it's quite important to evaluate the model in a way that matches well the application setting and in a way that stress tests the robustness of the model. So for instance, it's important to have the test data to be different enough from the trained data. We might want to avoid having repeated acquisition of the same individual in the train and the test, because this would not characterize our ability of the model to carry over to new individuals. And typically, it's often said these days that it's important to test the model on a fairly strong generalization. So generalizing to later in time, generalizing to new site. The reason we want to do this is we want to choose not only a model that gives us a small error, but also that's robust to some changes in the way the data arrives, because this may happen. And then another important point is that we want our test data to be representative of our target population, so of our target setting. So we might have sampling biases, we might have data that is available for training the model that actually differs from the data where we will apply the model. So ideally, we have a representative test set that's been acquired differently. If we don't have this representative test set, we might want to try to match things about the test set. So if I'm looking at individuals that have an age, and if my test set, say, has typically more young people than my trained set, I might, if my available data set has younger people than my target population, I may want to create a test set by putting more weight or oversampling the old population so as to have an equivalent distribution of age in my test set than in my target population. So basically rebalancing the test set to match the target population. Okay? That's the first point that I think is important. It's called external validation, for instance, in health research. Now, another point that I would like to stress is that our test set has a finite size. And so say I have 1,000 data points in my test set. These 1,000 data points are only 1,000 data points out of a full population. I could draw another 1,000 of data points, and I could evaluate my error metric on my first sample and my second sample. And so I could draw many of these. And as I draw many of these, I'm going to get different measures each time. And in the most simple model, if I'm just looking at accuracy, and my draws are independent, then I'm going to get a distribution of error that is described by a binomial distribution. And the point I'm trying to make here is that there is sampling noise. Each time I'm drawing a new test set, I'm going to get a different result. So a given test set is an imperfect estimate, an imperfect sample of the whole population, and so I should account for this sampling noise. Because if I'm comparing two models that have a difference between the two that is 0.1%, but my sampling noise is plus and minus 2%, which is the case for a test set of 1,000 data points, then I have no difference between the two. And I should probably take the model that is the simplest between the two. So really, the evaluation quality is limited by the number of test examples. Is this a problem in real life? Well, if you look at Kaggle competitions, and here we took Kaggle competition in the setting, in health setting, then what we can see is that the Kaggle competitions come with two different evaluation sets, the public and the private set. And we use these to estimate the evaluation error. And so what we can see is that the evaluation error is not small at all compared to the differences between, say, the best performing algorithm and the 10% best. So really, this evaluation error actually sometimes is bigger than the difference between the winners and the non-winners. So this evaluation error is not negligible at all. Goes back to an important point, which is that evaluation is often our bottleneck. We have a bunch of models, and we just don't have enough data to know which one is the best. So how can we have an idea of the uncertainty of our evaluation metric Well, we can look at confidence interval, and these are easy to compute for something like at least theoretically compute for something like a binomial accuracy, sorry, a binary accuracy or an accuracy-based metric. So because we can use binomial laws, and in our book chapter, we've given the confidence intervals for different size of test sets and different observed accuracy. And we hope that, so these are very easy to use. You just need to look them up in our book chapter, and we hope they'll be useful for you. Okay, so here I focused on the setting so far where I want to evaluate a prediction rule. So I have a fitted model, I want to put it in prediction, and I want to evaluate. But there is another setting where I am trying to evaluate a training procedure. The point being that I want to choose a training procedure that I might want to retrain one or many times. And now that's a different setting. And so the setting is, I'm given a procedure that takes training data and outputs a prediction. And the problem is that procedure comes with many arbitrary components, such as, for instance, the random states. So those are the seeds of the random number generator. And I want to stress that if I want to select the best training procedure, it's useless to tune the random seeds. It's useless, to try many random seeds out and take the one that performs best, because this will not carry over to new training data. So maybe we get a better prediction rule once, but give me new data. It's random. It will not carry over. So we did an empirical estimate of rerunning various evaluations many times, modifying arbitrary elements. And we did this in various application settings, including and a lot of deep learning in computer vision and natural language processing, but also standard machine learning in biomedical settings. And so what we saw was that, so those different arbitrary elements, such as weight inits, data order, data augmentation, all, have an impact on, all basically create noise in our evaluation. And so there's another arbitrary element. It's how did we split our data between train set and test set? And so we evaluate this also. It's the top line on the graph in red. And so what you can see is that this has actually more impact than all the other arbitrary elements. So our choice of train set and test set, or split, actually really creates noise in our evaluation procedure. So to get a better evaluation, ideally, we should sample multiple times these arbitrary choices. So if you want to select the best procedure, we should sample multiple times the split of the data in train and test set, the random inits, the data order, and all these things. We should sample it multiple times, and then we get multiple results, multiple estimation of error rates, and we average them. And by the way, when we sample multiple times, splitting between train and test, we're doing a well-known procedure that's known as cross-validation, and that unfortunately has fallen out of fashion, partly because it's expensive. But it gives better evaluation. So really what we want to do is we want to, do multiple train test split and randomize all arbitrary factors. Now, one of the challenges and one of the reasons why people often do not do that is that a full learning pipeline comes with hyperparameters. So things such as the amount of L2 regularization, or say the width of a neural network. And the way we typically set those hyperparameters is that we minimize the observed error on left out data. And so typically the way we work is that we, split out a test set that is going to be used to evaluate the model. We split out a validation set. We train the model multiple times on the train set, and we evaluate it on the validation set. We pick the best model, and this best model we evaluate it on the test set. So this is the way people do it. And one of the reasons why people do this is because the model choices are made in a manual way, and so they can't repeat them many times. But one danger here is that those model choices actually have a big impact on the performance of the pipeline. And so if we're comparing two pipelines and we've invested more effort or we've done a better job in choosing hyperparameter in one pipeline than the other, then this comparison becomes biased. And so what happens is that basically we have a human factor that's absolutely not controlled, which is how good was the human to choose hyperparameters on model A rather than model B. And if we want to conclude on the fact that, well, model A leads in general to better prediction rules than model B, we have here an uncontrolled element, which is this human factor. And so we're not concluding really on the model, we're concluding on the preference of the user and the model, which may or may not be a good thing. So one way around this is to use automated tuning of hyperparameters. And so I want to quickly cover how this can be done. Now, why is this important, by the way? I'll give you an example. A little while ago, we ran a competition to predict some neuropsychiatric disease, in particular autism, based on brain imaging. And so there were fairly strong incentives because the winner, I think, would get 5,000 euros. And so we gave a public data set to people for 3 months, and those people basically tried to select the best model on the public set. And then we evaluated this on the private set, which they didn't have. And so what you can see is that some people had excellent performing models on the public set, but those didn't carry over at all on the private set. And what happened is that those people did a lot of manual work and eventually overfitted the public set. So they got a performance that seemed good on the public set, but that was actually in the evaluation noise. And so there's good evidence that this happens often, and that the choice of hyperparameter on the model often leads to invalid conclusions. So to get around this, we can use hyperparameter optimization procedures. One approach is to do what's known as a grid search, is to vary each hyperparameter on a grid. So if I have 2 hyperparameters, I'm going to vary one on a grid, the other one on a grid. So basically, I'm going to get a set of values for parameter 1, set of values for parameter 2. I'm going to look at this on the test set, and I'm going to take the best the model that has the smallest error. So this is implemented in scikit-learn in Grid Search CV. But it may be more interesting to avoid varying the hyperparameters on the grid, because as you can see here, the grid is very regular. And if we have a region of good hyperparameter that is very narrow, it can fall between points. maybe another option is to use randomized sampling of the space, so what's known as random search, in which case what happens is that here we have one direction in which the optimal is very narrow, so an important hyperparameter, and another direction in which the optimum is much broader. And in this case, it's very interesting because as the points in both directions are not aligned, I get increased resolution on hyperparameter 1 as I sample hyperparameter 2. So in general, it's recommended to prefer random search to grid search if you have more than 2 hyperparameters to select. Okay, so if you want to do a good benchmarking procedure, you want to sample data sampling, so multiple train test split, all the arbitrary choices such as random seeds, and hyperparameter optimization. Now, one thing is quite often it's too expensive to rerun many times hyperparameter optimization. And so we've shown in a research paper that it's actually sometimes okay to run hyperparameter optimization once and then evaluate the resulting model on multiple train test splits and randomizing all the arbitrary choices. And one last thing I want to cover is that those model evaluations come with noise. They come with evaluation error. And so we might want to look at this evaluation error, and we might want to know whether, for instance, one model is significantly better than another. Now, an important point here is that if we've done multiple folds, the folds are not independent. So we can't use classic statistical testing. So we can't, take statistical tests, if you know what statistical tests are. We can't take statistical tests and apply them across the folds. So this is invalid. Likewise, we shouldn't be dividing the standard error by the number of folds. We shouldn't be dividing the standard deviation by the number of folds to get a standard error. In the interest of time, I'll skip this, and I'll just say that, I won't skip this, but I won't go too much into details, but I'll just say that one interesting view is to look at the standard deviation of a model evaluation. So I've rerun the folds many times. I've sampled the random seeds, and I've gotten, many different model evaluations. Many depends on my budget. Then I need to look at not only the average error observed, but also the standard deviation of the error. And the standard deviation is an interesting evaluation of the variation of model performance. And if I'm comparing two models, I have two models with two different standard deviations. And if those standard deviations overlap, it means that model A is going to outperform model B only a fraction of the times. And so typically a good rule of thumb is to say that model A is different enough from model B if the standard deviations, if the increment it gives on model B is larger than the standard deviation. And we might use this, for instance, if we have multiple models and they all perform within a standard deviation of each other, we might pick the one that leads to the less computing power because they're not really very different in practice. Or we might pick the one that is the most fair across different groups of individuals. So that gives decisions that are balanced between, say, men and women, and is not, much more accurate on men than women. It goes back to the point that I mentioned before, is that it's often important to account for multiple metrics when evaluating a model. Okay, so to wrap up, there are many sources of variance in model evaluation. One of them is data split, and it is typically the most important source of variance, but we should not underestimate that hyperparameter tuning can also change a lot the performance of a model, especially if it's done in a suboptimal way. I've stressed the fact that there are different use cases for model evaluation. One is to conclude on a fitted model, and another use case is to conclude on the fitting model. If I want to conclude on, one is to conclude on the fitted model, the other setting is to conclude on the fitting procedure. If I want to conclude on the fitted model, I should be using only a single train test split because I need one model to evaluate. If I want to be concluding on the fitting procedure, I need to sample many train test splits. And I want to stress that we want to focus on practical differences where the delta in performance is greater than the standard deviation obtained while across those multiple splits. We could discuss model evaluation longer. We could say that maybe it's good to have better experimental procedures. So to do somewhat systematic studies of the performance of the model, for instance, by changing specific aspects of the model and recording this, or doing learning curves. Learning curves is when I vary the amount of data available to my model and I look at how the performance varies. Okay, and once again, I've mentioned it before, your evaluation measure is intrinsically noisy because, for instance, of sampling noise, because of arbitrary choices. Keep this in mind and do not interpret improvements of models that are in the evaluation noise. And with this, I'll conclude. And I'll come back on the first points I made. The choice of performance metric should be suited to the application setting. And this requires a bit of thinking, for instance, on what we're interested in, probability of the ground truth given the prediction of the classifier. And more in general, I would like to think about evaluation and evaluation noise, because optimistic evaluation does not lead to good generalization. Thank you. I hope this was useful, sometimes leading to some thoughts, even with experienced machine learning practitioners. Thank you very much.
Thank you, Gaël, a lot. Actually, for me, you put together all the concepts. A lot of them we know about, we use them regularly, but it's very useful to step aside a bit, and to look at them once more time, to look and remember, okay, had this case and I had not make a cross validation and I got into trouble because it happened to me. Actually, it did, and also you were able to, for me personally, to kind of systemize, to systemize this knowledge. So thanks a lot for it. And from the audience, we have a bunch of questions. The most important one: how do you choose the features to release in new versions of scikit-learn library?
That's an interesting and a difficult question.
Yeah.
So there are different processes that come to play. Scikit-learn is a community-driven library, and that's something that's very important to us. So people who contribute code, help getting features in. So if somebody comes in with a feature and works a lot on it, there are more chances it gets in. That said, there still is a prioritization. We cannot take all the features. We would be drowning under code, and it would make an unmanageable libraries. So then we have first, the way this is scikit-learn is organized is that we have we have a set of people in the core team who make decisions, and we have a set of explicit inclusion criteria. So typically one thing that we don't do is that we do not take the latest published paper. And the reason we don't do this is that the latest published paper doesn't always generalize. So we have a rule that there needs to be a certain time between the published paper and when it comes in scikit-learn, and that also the paper must be cited a lot. And then we try to get some understanding of the users, and it's difficult because there are many different types of users, and we do this in informal informal back and forth with the user audience, typically at when we go to conferences, when we give tutorials, but also with targeted evaluation. We've had surveys, and we need to run more. And we also have private partners that give us money, and that's very useful. And we also listen to them. But it's important to stress that the private partners do not have their final say to what goes in scikit-learn. We listen to them, we listen to the community. Yeah, exactly.
Yeah, okay, cool. It's a community, and you also wait for some approach, some ideas, some to settle in, kind of to be rooted, to have also feedback from the community that it's useful, all the bugs fix it, and then you put it into production. Oh, cool.
We ask for empirical evidence, right? When there's a pull request, we want empirical evidence. We want an example that shows that this is useful.
Mm-hmm. And in your scikit-learn team, do you have Ukrainians? Like it's very common questions. Like Ukrainians, we want to be everywhere. We want to participate in everything and to develop everything. So do you have?
The first thing I should say is that we, in a sense, we must have actually several Ukrainians because it's a huge team and I don't know everybody. But I happen to know a Ukrainian. He does live in France, but Roman Yurcha is a contributor to scikit-learn and a friend. But he lives in Paris, and it's cheating. I'm pretty sure we have people who also live abroad, including in Ukraine.
Cool. It's glad to know that, and also that's the one from Dima. How to maximize such an interesting metrics? I mean, we still have limited loss functions, which have to be differentiable. So basically, if I understood Dima correctly, he wants to understand, okay, we know there is a bunch of chaos, a bunch of parameters to tune, a bunch of hidden biases in the data, a lot of stuff so how do look for the best, how to maximize towards the best metrics at the end. That's how I understood it, basically. I hope I understood it correctly, because for me it sounds like so Gaël, it's like when you are approaching a new problem and looking for selecting the best model and looking for selecting the best metrics suitable for the problem, suitable for the business, suitable for the data. How do you approach it? What's your goal, thought process?
Well, so I lost internet for a little while. So the original question I understood was basically, how do we, so here I've talked about model evaluation, but I think one of the questions was, okay, but how do we optimize the model for a given metric?
Yep.
Was that it? Yeah. Okay. So then it's related indeed to the choice of loss and losses. So the different metrics that I've presented are not, they're not, most of them are not usable as a loss, because the loss needs to have a bunch of properties. So many of our models actually do not, our models don't always enable a fine control of the loss. One thing that we do have in many models is sample weights or class weights that allow for what's known as cost-sensitive training, which allow for balancing the error on one class or the other, which is related to a metric that I didn't discuss, which is expected cost. It's basically an accuracy with weights, different weights on both classes. So that's one thing that we can readily do. With regard, so in the case of binary classification, so typically, the kind of metrics that we have are log loss or hinge loss and squared hinge loss. The thing is, when you're training a model, you also have a computational power that comes in mind, and you also have things like robustness that comes in mind. Because your model is not always well specified with regard to the data. So I would say that if you don't have computational questions in mind, I would always not use the hinge loss and always focus on something like a log loss. The reason is a bit technical. Okay, well, intuitively, the nice thing about the hinge loss is that it completely forgets part of the data. Anything that's well classified, far enough from well classified, it forgets. So in a sense, it's good because it makes the model more robust, but it also means that the model will not estimate a proper probability of the class given the data for a technical reason, which because the hinge loss is not what's known as a proper scoring rule, so it doesn't lead to selecting proper probabilistic models. And the hinge loss was historically introduced mostly for performance reasons. So, and now if we're looking at regression, which I did not discuss, then we might be interested in using the squared loss, which is the classic one, which leads to estimating the expected y given x. But we might also be looking at pinball losses, and the nice thing about the pinball loss is that it allows us to estimate the conditional percentile. And we've been adding pinball losses to more and more models in scikit-learn.
Okay, cool. That's important. That's important information because, like, when we approach any problem, it's a lot of decision to make, and we have to, and also we have time constraints. We have to make them optimal and have to be able to deliver to some date something consistent, something robust enough to be put further. And Bicola's question is kind of in the same direction. I understand we should use different metrics for different type of problems, but do you have some top metrics you are using always? What's your favorite ones? What's your go-to?
It's a good question. I don't actually really have a favorite one. I look at different things. It really depends on the application. However, if I don't know, I'll probably be using, if the classes are not too imbalanced, I'll be using a ROC AUC. And then I'll be looking probably at classification. So for instance, one thing I could do is for model selection, I could be using a ROC AUC and a Briar score. The ROC AUC is going to tell me that I have good thresholded metrics, the thresholded decision, and the Briar score is going to tell me that in addition, my non-thresholded value approximates well the probability of the class given the data. And so, for instance, I might, look at ROC AUC, take the best the model with the best ROC AUC, then use my one standard deviation rule to take out of, all the models that are within this rule, the one that has the best Briar score.
Okay, cool. It sounds like a solid baseline, like to look. And also in this direction, I had a question, not a question, but kind of a note. Once I met an article about Compass. Compass is they use it in the States in order to assign whether a convict is going to violate the parole or not. And it was the first time I met this calibration issue when the model is calibrated, but due to the huge biases in the data, it was not fair. It was not fair towards Americans, toward different races. people, and it was a huge story about it. Like they were trying to stop using the model, etc. And it was a huge exploration about how to understand that yes, the model is calibrated, but at the same time it's not fair. And calibrated doesn't mean that it's trustworthy. That's a different. So when I was listening for you about calibration, I was okay. I remember there was a huge implication about that, and it appeared to be more important than I thought. Oh, thanks for that. From Bogdan, we have a question that there is a paper that shows that seed number might matter, at least while training deep neural network. So Bogdan was looking for something to discuss with you, to have a small battle whether seed matters or not. So that's basically an abstract from the paper. So what do you think? Whether it makes some sense or it's just...
In a sense, I was referring to this paper because on the slide where I discussed the seed, I had the same exact number, 3407. This paper is an ironical paper. David wrote this paper by somewhat, stressing that we have a problem. And the problem that David wants to stress is that, if we're going to do optimizing for seed, we are going to get, one model that performs very well in a given test set. Now, that doesn't mean that the model performs very well on other test sets. We might have simply overfitted this test set. And B, it doesn't mean that given new training data, this model performs best. And once again, I'll draw the difference between selecting the best performing model and selecting the best performing training procedure. So selecting the best performing prediction rule and the best performing training procedure. If I'm interested in the best performing prediction rule, it's okay for me to try a bunch of seeds and take the one that performs best, because maybe I have some bad initializations and some good initializations.
Mm-hmm.
But if I retrain the data, my conclusion will not carry over. So it's meaningless. Now, maybe my training procedure, it's valid to have a training procedure that says, try 5 random seeds and pick the best one. In which case, it's part of my training procedure. But my full training procedure is try 5 random seeds and pick the best one. But if I'm comparing 2 models, and on one model I try 5 random seeds and I pick the best one, and not on the other, I'm not comparing those 2 models. I'm comparing 2 different training procedures.
Yeah. So it's really more like hacking.
And this will not generalize.
Yes, definitely. Yeah. It might work in one case or another, but not in the long run. Dmitro is asking about, I assume this one from our MLOps listeners. Are there any plans to incorporate GPU support for some scikit-learn algorithms like XGBoost, which already has GPU-based training?
So we're working on acceleration in 2 different directions. First, we're working on supporting fairly generic compute engines such as QPy or JAX, maybe inside some algorithms. Now, this will work with some algorithms, but not others. So typically, it won't accelerate tree-based models such as gradient boosting models. We're also slowly but surely working on making a pluggable infrastructure to allow plugging in optimized code. So the idea being, the vision being that hopefully in the near future, you'll install scikit-learn and then you'll install an optimizer that is related to the hardware you're running on. Could be GPUs, it could be TPUs. There are good reasons to think that in the near future we will see other kind of hardware accelerators. Now, give it a few years maybe to see this happening. I mean, it's in the process. It started, but before it starts being useful for most people, I don't know how long it'll take.
Thank you, but it's good to know that it's running, because as you mentioned, for cross validation, it's basically it's computing power which is lacking to make it more frequently used. Valeria is asking, which problems do you see in modern machine learning world? What appeared in your mind as their biggest issues, challenges, problems?
One of the big problems is that machine learning people, and whether it's in academia or industry, think too much about optimizing a number, an expected error, and do not think about how this, their prediction engine is going to fit in a bigger picture. What does this error mean? How does this prediction engine, how is it going to interact with other components? Most often, the prediction engine is given in a specific setting, and there's an interaction between this decision and the setting. And typically, this is why calibrated predictions are important, is that typically you might want, a prediction, but also the corresponding confidence, because you're going to make the decision differently. If it's in health, some decisions might impact user's life more than others. If I'm a pianist and I'm losing a finger, it's a disastrous thing. But maybe if I'm a teacher, it's maybe less important. And so there's always an interaction between the decision and the world beyond this. And the other thing is, that's maybe a bigger pet peeve, but the older I get, the more I get worried about the fact that technology is seldom the solution by itself. And when we have a problem, the good solution is always a mix of technological engineering and some sociological solution. And I really worry. Let's take, for instance, one example, which is climate change. I really worry that some people are dreaming about finding the solution to climate change, whatever it may be, electric cars or whatever. And so in the tech world, this makes us heroes. We're the people who do technology. We're going to save the world. And so it is almost a terrible like feedback loop where because we love this, we're tech people. We find that this person is a hero. We create our own bubble, and I almost worry that some managers, some important people are actually very happy that it happens, because then you can have people working in big companies, tech people working in big companies, that are optimizing metrics without thinking about the impact it has on the world. So this is maybe the problem I worry most about.
So, because these models, they do not exist in a vacuum. They do not exist just in a paper. But when they are applicable to something, they are starting to make an impact. So, and it's basically this feedback loop, and they basically could accelerate the biases, the errors by itself. If they learn these biases, they will be this feedback loop. Okay.
That's one example of problems.
Yeah. That's a problem to worry about. And Bogdan is interested. What's your favorite topic from technical background of your everyday tasks? In other words, what fascinates you the most about tech, math, of what you're doing?
So I guess from the very technical, maybe mathy or computer science topic, one of the things that fascinates me most about these days is the fact that many of the data we're interested in are made of a mixture of data of very different nature. So typically I'm interested in health and social sciences, so I'm going to be looking at individuals. Individuals are described by an age, a weight, maybe some different measures, but they also have a gender, a name, a country, where they come from, an address, a set, for instance, of pathologies, and all these things are discrete in some sense. And from a mathematical perspective, it's very hard to do joint modeling of those discrete objects that have different nature. A city and latest diagnosed pathology are discrete with a very different nature. So modeling all these things, they don't live in any form of regular space, not even a vector space. And there's a practice for the discrete object that historically comes from databases that's related to logic rules, which lead to the relational algebra. And this is how we handle databases. And then we have a practice that comes from statistics that's related to basically numerical vectors. And those don't fit together. So, from a very abstract perspective, math perspective, this is what fascinates me. And this is, I dedicate some of my time on this. But, what I think even more about these days when I have free time is the interplay between tech and society.
Oh, that's totally understandable, and I just think it fascinates all of us, practical implications and this edges when different areas are percolates each other and interconnects and influences each other, and how it's represented in from technical perspective. And I do know, Gaël, that you have a hard stop very soon, unfortunately, because we do have a few more questions. There were questions whether there are open position in your research group and others. And I want to thank. There are, yes, there are. So the ones who are asking that, you heard your answer. Thanks a lot for the topic. You brought about very important stuff. Sometimes it gets neglected in the rush for higher numbers, in the rush of delivering faster results. It gets neglected. And thanks a lot for the topic. Thanks a lot for the support. Because for us currently it's important. We feel involved in the international community more with that, and that was a very very intense and interesting hour for us. Thank you, and we will be glad that for moderator, I hope they will connect you later. Maybe we'll have another series later on the topic, because you mentioned that we're not talking about regression problems, etc. So there are a lot of topics also to cover. Thank you, and. So what's more? What we have for the next weeks, and also thank you guys a lot for a lot of questions for the Gaël, and for the next week. Next week we'll have a talk from Sebastian Babek from Microsoft. He will share his knowledge about unveiling transformers with Lego. And Lego, it's not the Lego you all thought about when you heard the name. It's abbreviation for learning equality and group operations. So register, donate, and you already answered your how do you find the session today? Thank you for that. It's important as a feedback for the community. Thank you for excellent and very good answers, rates of our work, and please donate. Please stay calm and stay hydrated. Also important. Till next week. Thank you. Bye, everyone.